For 35 years, humanity has believed a lie about Neptune. Every textbook, every documentary, every astronomy class, all of them have described Neptune as a deep, rich blue planet, sapphire in color, dramatically different from its neighbor Uranus. There's just one problem. That Neptune doesn't exist. The planet everyone has learned about since 1989 is a fabrication, not a mistake, a deliberate alteration by NASA's imaging team. And in 2024, scientists finally revealed the truth about what Neptune actually looks like. But the color deception is just the beginning, because Neptune has spent the last year rewriting everything scientists thought they knew. Magnetic fields that shouldn't be possible, Earth-sized storms that vanish into thin air, exotic molecules that can't form anywhere on Earth, underground oceans on captured moons, diamond rain falling through layers of superionic ice, temperature drops that defy explanation. This is the story of Neptune's greatest secrets, secrets that have only emerged in 2024 and 2025. Secrets that prove everything taught in schools needs to be completely rewritten. Welcome to the real Neptune. If discoveries like this excite you, if you want the real universe, not the classroom version, then you're in the right place. Here, we explore the breakthroughs reshaping space science in real time. Before we go further, tap like if you're ready to learn what school never mentioned. And subscribe so you never miss the mysteries we're uncovering next. Now, let's dive into Neptune's secrets, and we're starting with the biggest deception of all. Neptune has been blue for 35 years. Deep azure blue, the kind of rich sapphire color that made it instantly recognizable as the most distant planet in the solar system. At least, that's what everyone believed. The story begins in August 1989, when NASA's Voyager 2 spacecraft completed humanity's first and only flyby of Neptune. After a 12-year journey across 4.5 billion kilometers of space, Voyager 2's cameras captured the distant ice giant in unprecedented detail. But those cameras didn't work like human eyes. Voyager 2 captured separate images in different color filters, individual frames in red, green, and blue wavelengths. NASA's imaging team then had to combine these separate images into composite color pictures. And this is where the deception began. The team made a choice. They enhanced the images, stretched the colors, boosted the contrast. The goal was legitimate, to make Neptune's atmospheric features more visible. Cloud bands, storm systems, and wind patterns showed up far better in the enhanced images than they would have in true color. The result was a planet that looked far more blue than it actually was. NASA wasn't hiding this fact. The original press releases from 1989 included captions explaining that the images were enhanced. Scientists at the time knew the true color was different. The Voyager team was completely transparent about their image processing techniques. They published their methods. They explained their reasoning in scientific papers. But over time, those explanations were forgotten. The enhanced images spread through textbooks, documentaries, and museums. They became posters on bedroom walls. They appeared in encyclopedias and educational videos. They defined how an entire generation visualized Neptune. The images became the definitive representation of the planet. For 35 years, the artificially blue Neptune became the Neptune everyone knew. Meanwhile, Uranus presented a stark contrast. The images of Uranus from Voyager 2's 1986 flyby were processed closer to true color, showing a pale cyan appearance with hints of green. The two ice giants, similar in size, composition, and distance from the Sun, somehow looked dramatically different in color. Except they didn't. Not really. Amateur astronomers noticed the discrepancy. When they pointed their telescopes at Neptune and Uranus, the color difference wasn't nearly as dramatic as the famous Voyager images suggested. Both planets appeared as pale blue-green worlds, far more similar to each other than the public images indicated. Some astronomers spoke up about this. They published observations noting that Neptune didn't actually look as deeply blue as the Voyager images suggested. They pointed out that Uranus and Neptune should theoretically have similar colors, given their similar atmospheric compositions. But the enhanced Voyager images were so iconic, so widely reproduced, that they overshadowed these observations. The blue Neptune persisted in humanity's collective imagination. It was in every spacebook, every documentary, every educational material about the solar system, until 2024. In January 2024, a team of astronomers led by Patrick Irwin at the University of Oxford published groundbreaking research in the monthly notices of the Royal Astronomical Society. They had taken on an ambitious project, determining the true colors of Uranus and Neptune once and for all. The team used data from two powerful instruments. First, the Hubble Space Telescope's Space Telescope Imaging Spectrograph, which can measure the full spectrum of colors reflected from a planet. Second, the multi-unit spectroscopic explorer on the European Southern Observatory's Very Large Telescope in Chile, which provides similar spectroscopic data from ground-based observations. These instruments have a crucial advantage over the Voyager cameras. Instead of capturing separate color images that need to be combined, they record a continuous spectrum of wavelengths for each pixel. This allows astronomers to determine the precise, true color of what they're observing without any ambiguity or need for enhancement. The Oxford team used this data to reprocess the original Voyager 2 images, correcting for the color enhancements that had been applied 35 years earlier. They also analyzed more recent observations from Hubble's Wide Field Camera 3 to confirm their findings. The results shocked even the scientists involved. Neptune and Uranus are nearly identical in color. Both are pale greenish blue. Neptune has only a slight hint of additional blue compared to Uranus, caused by a slightly thinner haze layer in its atmosphere. But the dramatic difference everyone had believed in for decades, it never existed. The difference in appearance between the two planets is subtle, far more subtle than anyone had realized. If someone were to travel to the outer solar system and observe both planets with their own eyes, they would see two very similar-looking worlds. Both would appear as pale, almost pastel shades of greenish blue. The truth is that both ice giants have atmospheres dominated by hydrogen and helium, with about 2 to 3% methane. It's the methane that gives them their blue-green appearance. The gas absorbs red light and reflects blue and green wavelengths. With such similar atmospheric compositions, it makes perfect sense that they would appear similar in color. The enhanced Neptune images from 1989 had exaggerated this blue tint to make atmospheric features more visible for scientific study. Those features, the cloud bands, storm systems, and wind patterns, became indistinct and difficult to see in the true color images, which is exactly why NASA enhanced them in the first place. The Voyager imaging team was trying to maximize scientific return from a once-in-a-lifetime flyby. They were using image processing techniques that were standard in planetary science. They weren't trying to deceive anyone. They were trying to see Neptune's weather systems and atmospheric dynamics as clearly as possible. But the public never understood this distinction. The artificially saturated images became the reality in millions of minds worldwide. Teachers taught from textbooks showing the enhanced blue Neptune. Museum exhibits displayed the vivid imagery. Documentary narrators described Neptune's deep blue color as if it were unquestionable fact. The 2024 revelation forced a reckoning. Textbooks would need updates. Documentaries would need corrections. Museum displays would need revisions. Educational websites would need to change their descriptions. The Neptune that humanity thought it knew for 35 years had been, in essence, a carefully constructed illusion. Professor Patrick Irwin explained in interviews that even he was surprised by how similar the two planets actually are. The research team had expected to find some difference in color, But the reality was that Neptune and Uranus are nearly twins in appearance. This wasn't the first time enhanced planetary images had created misconceptions. Mars faces similar issues. Its surface appears much redder in enhanced images than it does to the human eye. The famous red planet is actually more of a butterscotch color in reality. But Neptune's case was particularly striking because of how long the misconception persisted and how thoroughly it had been accepted as fact. The color correction also solved another mystery that had puzzled astronomers for decades. Scientists had long wondered why Uranus's color appeared to change subtly over the course of its 84-year orbit around the Sun. Using observations from Arizona's Lowell Observatory dating back to 1950, the Oxford team discovered that Uranus appears slightly greener at its solstices, when one of its poles points toward the Sun, and slightly bluer at its equinoxes. The explanation involves seasonal changes in atmospheric haze. During solstices, increased methane ice particles form over the sunlit pole, creating a brighter, more reflective haze layer. This haze scatters more green and red light, making the planet appear greener. During equinoxes, with more uniform sunlight distribution, the planet appears bluer. These subtle variations had been masked by the dramatically enhanced color images. Only with the true color data could scientists finally understand what was actually happening in these distant atmospheres over the course of Uranus's long seasons. The color revelation matters for more than just correcting the public record. Scientists studying exoplanets, planets around other stars, often try to determine their compositions based on their colors and spectra. Understanding the true colors of Neptune and Uranus provides crucial reference points for interpreting observations of distant Neptune-like exoplanets. And Neptune-like exoplanets are incredibly common. In fact, they're among the most frequently discovered types of planets in the galaxy. Thousands of Neptune-sized worlds have been found orbiting other stars. Getting the colors right helps astronomers understand what these distant worlds might actually be like and what their atmospheres might contain. The color deception also raises important questions about scientific communication. How do scientists balance the need for enhanced images that reveal scientific details with the public's desire for true representations of what these worlds look like? When do legitimate enhancements cross the line into creating false impressions? These questions remain debated in the planetary science community. Some argue that enhanced images should always be labeled more clearly. Others point out that all astronomical images are, to some degree, false color representations because they often include wavelengths invisible to human eyes. But one thing is certain: Neptune is no longer the deep blue planet of textbooks and documentaries. It's a pale greenish-blue world, nearly identical to its neighboring ice giant Uranus. After 35 years, humanity finally knows what Neptune actually looks like. But here's the unsettling part. If scientists got Neptune's color wrong for 35 years, what else about this distant planet has been misunderstood? As it turns out, quite a lot. Because beneath Neptune's misrepresented atmosphere lies something far stranger. Something that defies the fundamental laws of physics as scientists understand them. Neptune's magnetic field shouldn't exist. And until November 2024, no one could explain why it does. When Voyager 2's magnetometer detected Neptune's magnetic field in August 1989, the readings made absolutely no sense. Earth's magnetic field is straightforward. A molten iron core spins deep inside the planet, generating a dipole field with north and south magnetic poles aligned roughly with the planet's rotational axis. It's the same basic configuration as a bar magnet. Field lines emerge from one pole, curve around the planet, and enter at the opposite pole. Jupiter and Saturn work the same way. Their magnetic fields are generated by electrically conducting liquid metallic hydrogen deep in their interiors. The fields are strong, stable, and aligned reasonably well with their rotation axes. Neptune's field is chaos. The magnetic field is tilted 47 degrees from the planet's rotational axis. To understand how extreme this is, imagine if Earth's magnetic North Pole were located somewhere in the middle of the Indian Ocean. That's the level of misalignment scientists encountered on Neptune. But the tilt is just the beginning of the strangeness. The field is also offset from Neptune's center by 55% of the planet's radius. This means the center of the magnetic field, the point from which the field appears to originate, is actually closer to Neptune's cloud tops than it is to the planet's core. It's as if the magnetic field is generated in a shell-like layer somewhere in the middle of the planet, rather than deep in the core where planetary magnetic fields are supposed to originate. And unlike the relatively simple dipole fields of Earth, Jupiter, and Saturn, Neptune's magnetic field is multipolar. Instead of two well-defined magnetic poles, Neptune has multiple magnetic poles scattered across its surface. The field lines don't follow orderly paths from pole to pole. They loop in and out of the planet at various latitudes in a tangled, chaotic pattern. For scientists accustomed to the orderly magnetic fields of other planets, Neptune's magnetism was shocking. When Voyager 2 first discovered a similarly strange magnetic field at Uranus in January 1986, planetary scientists initially thought it might be explained by Uranus's extreme axial tilt. Uranus rotates on its side, with its rotation axis tilted 98 degrees. Perhaps, scientists theorized, this unusual orientation somehow disrupted the normal magnetic field generation process. But then, Voyager 2 arrived at Neptune 3.5 years later and found essentially the same magnetic field configuration. Neptune's axial tilt is normal, only 28 degrees, similar to Earth's 23-degree tilt. Yet its magnetic field was just as chaotic and misaligned as Uranus's. The Uranus explanation was wrong. Something else was causing these bizarre magnetic fields. The Voyager 2 data forced planetary scientists to completely reconsider how magnetic fields could be generated inside planets. The discovery challenged fundamental assumptions about planetary interiors and magnetic dynamo processes. Why do magnetic fields matter so much? Planetary magnetic fields serve crucial functions. They protect planets from solar wind, the constant stream of charged particles flowing outward from the sun. Without a magnetic field, solar wind would strip away a planet's atmosphere over millions of years. Mars lost most of its atmosphere this way after its magnetic field shut down billions of years ago. Magnetic fields also reveal what's happening deep inside planets. The structure and strength of a magnetic field provides clues about a planet's internal composition, temperature, and dynamics. By studying magnetic fields, scientists can effectively see inside planets in ways that would otherwise be impossible. And for the search for habitable worlds beyond Earth, magnetic fields might be essential. A strong magnetic field could be a requirement for a planet to maintain a stable atmosphere capable of supporting life. So understanding why Neptune and Uranus have such unusual magnetic fields isn't just an academic curiosity. It's fundamental to understanding how planets work and what conditions might support life elsewhere in the universe. For decades after the Voyager 2 flybys, scientists proposed various theories to explain the ice giant's strange magnetism. In 2004, planetary scientists Sabine Stanley and Jeremy Bloxham from Harvard University published an influential theory. They proposed that Neptune and Uranus might have layered interiors that don't convect uniformly. Unlike Earth, where the entire outer core convects and generates a dipole field, these ice giants might only generate magnetic fields in a thin shell near the surface. The Stanley-Bloxham model suggested that the magnetic field originates in a thin convecting layer of electrically conducting fluid, probably water mixed with ammonia and other compounds, while the deep interior remains magnetically inactive. This thin-shell dynamo would naturally produce a more chaotic, multipolar field instead of a simple dipole. The model made sense theoretically, but it left a crucial question unanswered. What creates this layered structure? Why would the interior of Neptune separate into a magnetically active shell and an inactive deep interior? For 20 years, no one had a satisfying answer. Then came the breakthroughs of 2024. In May 2024, a team of scientists from Skoltech in Russia and Chinese research institutions published remarkable findings in the journal Physical Review B. They had been using advanced computational models to simulate conditions inside ice giant planets under extreme pressure and temperature. The researchers discovered something extraordinary, an exotic molecule that can form in Neptune's interior but nowhere on Earth. The molecule is called aquadium. Its chemical formula is H4O2+. It consists of 4 hydrogen atoms bonded to 1 oxygen atom with a net positive charge. Aquadium is essentially a water molecule, H2O, with 2 additional protons stuck to it. Under normal conditions, this molecule is extremely unstable and would immediately fall apart. The energy barrier to adding a second proton to hydronium, H3O+, which is water with 1 added proton, is simply too high under Earth-like conditions. But deep inside Neptune and Uranus, conditions are anything but Earth-like. At depths of about 12,000 kilometers below the cloud tops, pressures reach millions of atmospheres. Temperatures soar to thousands of degrees. And in the presence of small amounts of acid, these conditions can stabilize aquadium. The discovery was remarkable because aquadium can conduct electricity, and conducting fluids in motion are exactly what generate planetary magnetic fields. The researchers calculated that aquadium, along with other ions like hydronium and ammonium, could exist in a water-rich layer deep inside Neptune. As this layer convects, hot material rising, cool material sinking, the ions would move, generating electrical currents. These currents would produce the chaotic magnetic field observed by Voyager 2. But the May 2024 discovery was just the beginning. In November 2024, another breakthrough emerged. Burkhard Militzer, a planetary scientist at the University of California, Berkeley, published groundbreaking research in the Proceedings of the National Academy of Sciences that finally explained why Neptune and Uranus have layered interiors. Militzer ran sophisticated computer simulations of the behavior of water, methane, and ammonia, the primary components of ice giant interiors, under the extreme pressures and temperatures found inside these planets. The simulations revealed something unexpected. These materials don't mix. Under the conditions inside Neptune and Uranus, water, methane, and ammonia undergo a process called phase separation. Like oil and water, they spontaneously separate into distinct layers. The upper layer becomes water-rich. This layer convects vigorously, with hot water rising from below and cooler water sinking from above. And crucially, this is where the magnetic field is generated. The lower layer becomes rich in carbon, nitrogen, and hydrogen. As pressure increases with depth, the methane and ammonia in this layer transform into something bizarre, a polymeric fluid consisting of carbon, nitrogen, hydrogen chains. This material doesn't conduct electricity well and doesn't convect. It's magnetically dead. Even more remarkably, Militzer's simulations showed that as the carbon, nitrogen, hydrogen material sinks deeper into the planet, it progressively loses hydrogen atoms. The carbon and nitrogen form increasingly complex polymers. At the depths where this happens, the conditions are perfect for the formation of diamonds. The sinking polymeric material reaches regions where carbon separates out and crystallizes into pure diamond. These diamonds then sink even further, pulled downward by gravity because they're denser than the surrounding fluid. This is the origin of Neptune's diamond rain. a phenomenon scientists had speculated about for decades but never fully understood. The November 2024 breakthrough brought everything together. Neptune and Uranus have phase-separated interiors. A water-rich upper layer generates the chaotic magnetic field. A carbon-rich lower layer remains stratified and magnetically inactive. And diamonds form at the boundary between these layers, raining downward through the planet's interior. The implications are profound. First, it explains the magnetic field mystery that has puzzled scientists for 35 years. The thin, convecting water layer generates magnetism, but without the stabilizing influence of a solid inner core, the field remains chaotic and multipolar. Second, it reveals that Neptune and Uranus have vast oceans of water in their interiors. Not liquid water in the sense of Earth's oceans. These are hot, dense, superionic water oceans existing under crushing pressure. But they're water nonetheless, existing in states that can't be reproduced on Earth. Third, it shows that diamond formation is happening continuously inside these planets. As methane and other hydrocarbons break down under pressure, carbon atoms separate out and form diamonds. These diamonds grow as they sink, potentially reaching enormous sizes, perhaps millions of carats in weight. In January 2024, just weeks after Militzer's breakthrough, another research team published findings in Nature Astronomy that confirmed diamond rain occurs at even shallower depths than previously thought. Using the European X-ray free electron laser facility in Germany, scientists led by Mungo Frost from SLAC National Accelerator Laboratory in California recreated the conditions inside ice giants. They used polystyrene, plastic, as a substitute for the hydrocarbons found in Neptune's atmosphere. When subjected to extreme pressure and temperature, nearly every carbon atom in the plastic transformed into nanodiamonds within nanoseconds. The experiment showed that diamond formation begins at pressures and temperatures corresponding to depths of only a few thousand kilometers inside Neptune and Uranus, much shallower than previous estimates of 8,000 to 10,000 kilometers. This means diamond rain is occurring in the same region where the magnetic field is generated. As diamonds form and sink through the convecting water layer, they stir the conducting fluids, potentially enhancing the dynamo effect that produces magnetism. The Frost team also calculated that on Neptune and Uranus, where these conditions persist for millions of years, diamonds would grow to enormous sizes. Meter-sized diamond crystals are entirely plausible. Some diamonds might grow even larger, reaching dimensions of tens or even hundreds of meters. These discoveries about Neptune's interior have implications far beyond our solar system. Neptune-sized planets are the most common type of exoplanet discovered so far. Thousands of Neptune-like worlds orbit other stars. Many are mini-Neptunes, smaller than Neptune but larger than Earth. And these planets don't exist in our solar system at all. Understanding Neptune's interior helps scientists interpret observations of these distant worlds. If a Neptune-sized exoplanet has a chaotic magnetic field, scientists now know this likely indicates a phase-separated interior with a thin convecting shell generating the magnetism. The magnetic field also affects habitability. A planet's magnetic field protects any moons orbiting that planet from radiation. Neptune's moon Triton, which may have a subsurface ocean potentially capable of supporting life, exists within Neptune's magnetosphere. Understanding how that magnetosphere works is crucial for assessing Triton's habitability. The November 2024 breakthrough represents one of the most significant advances in planetary science in recent years. For the first time, scientists understand why Neptune and Uranus are so different from other planets. They know why the magnetic fields are chaotic. They know what the interior structure looks like. They know how diamonds form and rain through the planet's depths. Neptune's interior is a realm of extremes that pushes the boundaries of what scientists thought possible. Exotic molecules that can't exist on Earth. Phase separation creating distinct chemical layers. Vast oceans of superionic water. diamond rain falling through convecting fluid shells, chaotic magnetic fields generated by processes unlike anything found on other planets. But Neptune's strangeness doesn't end with its interior and magnetic field. Because on this distant world, the atmosphere itself defies expectations. Storms the size of Earth appear from nowhere, then vanish completely, as if they never existed at all. On August 25, 1989, Voyager 2 captured images of Neptune's atmosphere that stunned planetary scientists. There, in the planet's southern hemisphere, churned a massive storm system. Scientists named it the Great Dark Spot, a clear parallel to Jupiter's famous Great Red Spot. The Great Dark Spot was enormous. It measured roughly 13,000 kilometers by 6,600 kilometers, large enough to contain the entire Earth. The storm rotated counterclockwise, spinning in an anticyclonic pattern. Wind speeds at the storm's edge reached 2,400 kilometers per hour, the fastest planetary winds ever recorded in the solar system. The storm appeared dark because it was actually a depression in Neptune's cloud deck. Instead of towering clouds like those in Jupiter's Great Red Spot, the Great Dark Spot was a deep vortex where clouds had cleared away, revealing darker atmospheric layers beneath. Accompanying the Great Dark Spot were bright white companion clouds. These clouds formed as atmospheric gases flowed up and over the vortex, cooling as they rose and condensing into methane ice crystals. The bright clouds stretched for thousands of kilometers, riding along the edge of the dark storm. Voyager 2 also observed a smaller storm, designated Small Dark Spot or Dark Spot 2. This second storm, located further south, was about 2,000 kilometers across. As Voyager 2 approached Neptune, astronomers watched this smaller storm change dramatically, brightening and darkening over the course of days. The existence of these massive storms was surprising. Neptune receives only about 1/900th the sunlight that Earth receives. At such a distance from the Sun, the energy available to drive atmospheric dynamics should be minimal. Yet here were planet-wide storm systems with winds far more powerful than anything found on Earth or even Jupiter. One NASA analyst, Ken Bollinger, commented during the Voyager 2 flyby, "Every day what you see is brand new. Nobody's ever seen it. It's just an incredible feeling. There are changes going on constantly on Neptune that happen very, very fast." Scientists were eager to continue observing these storms and understand how they evolved. Would the Great Dark Spot become a permanent feature like Jupiter's Great Red Spot, which has persisted for at least 300 years and possibly much longer? But when the Hubble Space Telescope was launched in April 1990 and commissioned for observations, astronomers had an opportunity to check on Neptune's storms. In 1994, Hubble was pointed at Neptune. The Great Dark Spot had completely vanished. Not shrunk, not faded, vanished. Gone. As if it had never existed. Dark Spot 2 had also disappeared. Planetary scientists were stunned. They had expected the storms to change slowly, perhaps evolving over years or decades. Jupiter's Great Red Spot has been observed for centuries without disappearing. Saturn's storms can last for months or years. But Neptune's storms had lifespans measured in just a few years. The disappearance raised immediate questions. Had the storms actually dissipated, or had they simply moved to a region of Neptune not visible from Earth? If they had genuinely disappeared, what mechanism could cause such a massive atmospheric feature to vanish so quickly? Hubble continued to monitor Neptune over the following years. In 1996, a new dark spot appeared, this time in Neptune's northern hemisphere. Designated Northern Dark Spot 1994, this storm exhibited stability in latitude, but eventually disappeared sometime between 1998 and 2000. In 2002, another northern dark spot was observed. Then in 2015, Hubble captured yet another dark spot forming in the southern hemisphere. A pattern emerged. Neptune's atmosphere generates these massive dark spots regularly, but they only persist for a few years before vanishing. In 2018, Hubble observed something remarkable: a dark storm forming from its very beginning. For the first time, astronomers could watch a great dark spot emerge and document its birth. The 2018 storm, designated Northern Great Dark Spot 2018, appeared in Neptune's northern hemisphere at a latitude of 23 degrees north. It measured roughly 11,000 kilometers by 5,000 kilometers, comparable in size to the original Great Dark Spot observed by Voyager 2. Planetary scientist Amy Simon from NASA's Goddard Space Flight Center was monitoring Neptune as part of the Outer Planet Atmosphere's Legacy Program, OPAL for short, a long-term Hubble project to observe the outer planets annually. Simon and her team searched through Hubble images taken in the years before the storm's appearance. They found something intriguing. Bright white companion clouds had appeared in the region 2 to 3 years before the dark spot became visible. This suggested that dark spots don't form suddenly. Instead, they develop over several years, with atmospheric changes occurring deep in Neptune's atmosphere before the dark spot becomes visible in the blue wavelengths where Hubble can detect them. The 2018 storm provided scientists with their best opportunity yet to study how these mysterious vortices behave. Hubble tracked the storm as it drifted westward at about 2.5 degrees per hour, slower than the surrounding atmospheric winds. Then, in 2020, something unexpected happened. The storm, which had been drifting southward toward Neptune's equator, where models predicted it would dissipate, suddenly reversed direction. It began moving northward, back toward higher latitudes. This behavior had never been observed before. Planetary models suggested that dark spots should drift toward the equator and disappear when they reach low latitudes. The 2018 storm was following this pattern until it abruptly wasn't. In January 2020, Hubble spotted something else. A smaller dark spot had appeared near the larger storm. This smaller feature was about 6,500 kilometers across, roughly the size of Earth's Atlantic Ocean. Scientists speculated that this smaller spot might be a fragment that broke off from the larger storm. Perhaps the main vortex was undergoing disruption, shedding pieces as it evolved. Michael Wong, a planetary scientist at the University of California, Berkeley, and member of the OPAL team, explained, "We are excited about these observations because this smaller dark fragment is potentially part of the dark spot's disruption process. This is a process that's never been observed. We have seen some other dark spots fading away, and they're gone, but we've never seen anything disrupt, even though it's predicted in computer simulations." The smaller spot appeared briefly and then vanished, possibly drifting away or dispersing into the surrounding atmosphere. The behavior of Neptune's dark spots remains only partially understood. Scientists have several competing theories about their formation and disappearance, but no single explanation accounts for all observed behavior. One theory suggests that dark spots form when wind bands at different latitudes, moving at different speeds, create shear zones where vortices can develop. Once a vortex forms, it can drift between the wind bands, persisting as long as it remains in a favorable region. Another theory focuses on deeper atmospheric dynamics. Neptune's internal heat drives vigorous convection from deep in the atmosphere. When particularly strong convection cells rise toward the surface, they might create conditions favorable for vortex formation. The fact that bright companion clouds appear years before the dark spots themselves become visible supports this deep origin theory. The clouds might form when deep atmospheric disturbances push gases upward, cooling them and causing methane ice to condense. But why do the storms disappear so quickly compared to Jupiter's centuries-old Great Red Spot? The answer likely involves multiple factors. Neptune's atmosphere is far more dynamic than Jupiter's. Neptune radiates 2.6 times more energy than it receives from the Sun, creating vigorous internal heating that drives atmospheric circulation. Jupiter also has internal heat, but not to the same degree relative to solar input. Neptune's faster winds, up to 2,100 kilometers per hour at the equator, create stronger wind shear. This shear might eventually tear apart storm systems that would remain stable in Jupiter's more orderly atmosphere. The chemistry of Neptune's atmosphere might also play a role. Neptune's clouds consist primarily of methane ice, while Jupiter's clouds are made of ammonia ice and other compounds. These different cloud compositions might affect how storms evolve and dissipate. In August 2023, astronomers achieved something remarkable. They detected a dark spot on Neptune from ground-based telescopes for the first time ever. Using the Very Large Telescope in Chile, specifically its multi-unit spectroscopic explorer instrument, Patrick Irwin's team at Oxford University observed a dark spot in Neptune's atmosphere and obtained spectroscopic data revealing its composition and structure. The ground-based detection was significant because it demonstrated that these features could now be studied without relying solely on Hubble. The Very Large Telescope's capabilities had advanced to the point where Neptune's atmospheric features were accessible from Earth. The spectroscopic data provided crucial new information about what dark spots actually are. Previous observations could only see the spots at blue wavelengths, where they appeared dark against Neptune's brighter background. But spectroscopy reveals information across many wavelengths, providing clues about atmospheric composition and structure. The 2023 observations indicated that dark spots are likely caused by air particles darkening in a layer below the main visible haze layer. As ices and hazes mix in Neptune's atmosphere at specific depths, they create regions where atmospheric particles absorb more light, appearing as dark spots when viewed from above. This contradicted an earlier theory that dark spots were simply clearings in Neptune's cloud deck, holes where clouds had dispersed, revealing darker layers beneath. Instead, they appear to be regions where atmospheric chemistry creates darker particles at a specific altitude. The research team also discovered something unexpected: a bright spot accompanying the dark spot, but at the same atmospheric depth rather than at higher altitude like the companion clouds. They named it a deep, bright cloud, a feature never identified before, even from space. Scientists still don't fully understand what causes this deep, bright cloud, or how it relates to the dark spot formation process. By 2024, the dark spot observed in 2015 had completely disappeared. Like all of its predecessors, it had persisted for a few years and then vanished without a trace. Computer simulations by Amy Simon's team attempted to predict how often dark spots should appear on Neptune. The simulation suggested that at any given time, there's about a 60% chance that a dark spot exists somewhere on Neptune, though not all spots will be visible from Earth, depending on which hemisphere is tilted toward us. Over the course of a Neptunian year, 165 Earth years, the simulations predicted numerous dark spots would form and dissipate. Hubble's observations since 1994 roughly match these predictions, though the sample size is still small given Neptune's long orbital period. The mystery of Neptune's dark spots highlights how little humanity actually knows about this distant world. These are planet-sized features, storms as large as Earth itself, yet scientists can't predict when they'll appear, how long they'll last, or why they disappear. The contrast with Jupiter is striking. Jupiter's Great Red Spot has been observed telescopically since at least 1665, and possibly much earlier. It's a stable, persistent feature that planetary scientists can study continuously. Its behavior is reasonably well understood. Neptune's storms, by comparison, are ghosts. They appear without warning, rage through the atmosphere for a few years, with the most violent winds in the solar system, and then vanish as mysteriously as they arrived. This unpredictability makes Neptune's atmosphere one of the most enigmatic in the solar system. Despite having only 1,000th the solar energy input of Earth, Neptune generates weather more violent and dynamic than anything found on the inner planets. And the atmospheric mysteries don't end with vanishing storms, because in March 2025, the James Webb Space Telescope captured something even more unexpected: auroras stretching across Neptune's atmosphere in places they shouldn't exist. Auroras glowing in temperatures so cold they should be impossible to detect. Neptune's atmosphere continues to surprise scientists with phenomena that defy explanation. In March 2025, the James Webb Space Telescope released images that stunned the astronomical community. Neptune was glowing. Not brightly. These were faint emissions in the near-infrared spectrum, invisible to human eyes. But there they were, auroras stretching across Neptune's mid-latitudes, shimmering bands of light caused by charged particles interacting with the atmosphere. For decades, scientists had theorized that Neptune must have auroras. Every planet with a magnetic field and an atmosphere should produce auroral emissions when charged particles from the solar wind spiral along magnetic field lines into the upper atmosphere. Earth has auroras, the northern and southern lights. Jupiter has spectacular auroras visible in ultraviolet and infrared. Saturn has them too, but actually detecting Neptune's auroras had proven nearly impossible. When Voyager 2 flew past Neptune in 1989, its instruments detected evidence of charged particles in the magnetosphere that should produce auroral activity. But the spacecraft never directly observed the auroras themselves. The emissions were simply too faint at the wavelengths Voyager could observe. For 35 years, Neptune's auroras remained theoretical, predicted by physics, but never actually seen. Until Webb changed everything. The James Webb Space Telescope, which launched in December 2021 and began science operations in July 2022, represents the most powerful infrared observatory ever placed in space. Its sensitivity to infrared light is orders of magnitude better than previous telescopes. In June 2023, Webb turned its near-infrared spectrograph toward Neptune. The observation was part of a broader program to study ice giant atmospheres using Webb's unprecedented capabilities. The data revealed emissions from triatomic hydrogen ions, written as H3+. These ions form when molecular hydrogen, H2, is struck by high-energy particles, knocking off an electron and allowing a third hydrogen atom to bond with the molecule. H3+ only exists under extreme conditions. On Earth, it's created briefly in laboratory experiments or in the high atmosphere during intense auroral storms. But on Neptune, Webb detected H3+ emissions spanning across large regions of the planet. These emissions were auroras, proof that Neptune's magnetosphere was channeling charged particles into the atmosphere, exciting atmospheric gases and causing them to glow. But the auroras weren't where scientists expected them to be. On Earth, auroras occur near the magnetic poles, the northern lights in the Arctic and southern lights in the Antarctic. This happens because Earth's magnetic field lines converge at the poles, funneling charged particles from space into these high-latitude regions. Jupiter and Saturn also have polar auroras. The auroral ovals on these planets circle their magnetic poles, creating spectacular light shows in the ultraviolet and infrared. Neptune's auroras were different. Instead of concentrating at the poles, Neptune's auroral emissions stretched across mid-latitudes, roughly between 30 and 60 degrees from the equator. The emissions formed bands and patches scattered across the planet rather than neat ovals around the poles. This strange distribution is a direct consequence of Neptune's bizarre magnetic field. Remember that Neptune's magnetic field is tilted 47 degrees from its rotation axis and offset from the planet's center. This creates a complex, multipolar field structure where magnetic field lines don't simply loop from pole to pole. Instead, field lines emerge from and plunge back into Neptune at various latitudes. Charged particles following these field lines can enter the atmosphere at mid-latitudes rather than just at the poles. The result is auroral activity spread across much of the planet. a phenomenon completely unlike the neat polar auroras of Earth and the gas giants. But detecting these auroras raised another question. Why had they been so difficult to observe for so long? The answer lies in Neptune's atmospheric temperature. Webb didn't just detect auroras in 2023. It also measured temperatures in Neptune's upper atmosphere. And those temperatures were shockingly low. Neptune's thermosphere, the uppermost layer of the atmosphere where auroras occur, had temperatures around 450 Kelvin. That's roughly 177 degrees Celsius, or 350 degrees Fahrenheit. This might sound hot by Earth standards, but it's actually extraordinarily cold for a planetary thermosphere. Earth's thermosphere can reach temperatures of 1500 Kelvin or higher during solar activity. Jupiter's thermosphere exceeds 1000 Kelvin. Even more remarkably, Webb's measurements were significantly lower than readings taken by Voyager 2 in 1989. Voyager 2 had measured thermospheric temperatures around 750 Kelvin. Neptune's upper atmosphere had cooled by about 300 degrees in the 36 years between Voyager 2 and Webb observations. This temperature drop is completely unexplained. The thermosphere's temperature is determined by how much energy is deposited there, from solar ultraviolet radiation, from auroral particle precipitation, and from atmospheric waves propagating upward from below. None of these energy sources should have changed dramatically over 36 years. The Sun goes through 11-year activity cycles, but Neptune's distance means solar variation has minimal effect on its atmosphere. Auroral activity might vary, but not enough to explain a 300-degree temperature change. And internal atmospheric waves should remain relatively constant. Yet somehow, Neptune's thermosphere lost a tremendous amount of thermal energy between 1989 and 2023. This cooling might help explain why Neptune's auroras are so faint and difficult to detect. Auroral emissions depend on both the number of particles hitting the atmosphere and the temperature and density of the atmospheric gases. Colder, less dense atmospheres produce dimmer auroras. The cooling might also be connected to Neptune's magnetic field behavior. If the magnetic field structure changed between 1989 and 2023, shifting the locations where field lines connect to the atmosphere, it could alter how efficiently charged particles are deposited in the thermosphere. But scientists don't know if or how Neptune's magnetic field might be changing. Unlike Earth, where magnetic field measurements are made continuously from ground stations and satellites, Neptune's magnetic field has only been measured once, during Voyager 2's brief flyby. The Webb observations also revealed another mystery about Neptune's auroras. They're incredibly variable. Unlike Earth's auroras, which respond relatively quickly to changes in solar wind conditions, Neptune's auroral emissions appeared to fluctuate on timescales of hours or days for reasons scientists couldn't immediately identify. This variability might be connected to Neptune's rotation. The planet rotates once every 16 hours, and the tilted, offset magnetic field rotates with it. As different parts of the magnetosphere rotate into view, the auroral emissions might change intensity. Or the variability might indicate that Neptune's magnetosphere itself is highly dynamic, with the configuration of magnetic field lines and trapped particles constantly shifting. The 2025 Webb observations represented the most detailed study of Neptune's auroras ever conducted. But they also generated more questions than answers. Why is the thermosphere so cold? What caused the dramatic cooling since Voyager 2? How does the unusual magnetic field structure affect auroral particle precipitation? Why are the emissions so variable? And perhaps most intriguingly, if Neptune's auroras are this faint and difficult to detect, what other atmospheric phenomena might be occurring that scientists simply haven't been able to observe yet? Neptune sits 4.5 billion kilometers from Earth. Even with the most powerful telescopes ever built, studying this distant world remains extraordinarily challenging. Every observation provides tantalizing glimpses of phenomena occurring in Neptune's atmosphere, but comprehensive understanding remains elusive. The auroral discoveries of 2025 mark a significant milestone, finally confirming that Neptune has auroras and beginning to understand how they differ from auroras on other planets. But they also highlight how much remains unknown about Neptune's upper atmosphere and magnetosphere. Scientists hope to continue monitoring Neptune with Webb over coming years, tracking how the auroral emissions change with time and searching for patterns that might explain their behavior. Ground-based telescopes are also improving. The Very Large Telescope in Chile and other major observatories now have instruments sensitive enough to potentially detect Neptune's H3+ emissions from Earth, allowing for more frequent monitoring than Webb's limited observation time permits. But ultimately, truly understanding Neptune's auroras will require returning to the planet with a dedicated spacecraft, something that hasn't happened since Voyager 2's brief encounter 36 years ago. And Neptune's atmospheric mysteries extend beyond auroras and vanishing storms. Because the violent weather, the magnetic chaos, and the ghostly auroral emissions are all driven by something deep inside the planet, an energy source that shouldn't exist. Neptune radiates 2.6 times more energy into space than it receives from the Sun. This simple fact has profound implications. The Sun is Neptune's star, its source of light and heat. At Neptune's distance of 30 astronomical units, 4.5 billion kilometers, solar energy is incredibly weak. Neptune receives only 1/900th the sunlight that Earth receives. At such a distance, Neptune should be cold and inactive. Its atmosphere should be calm, dominated by slow seasonal changes as different hemispheres receive marginally more or less of the Sun's feeble warmth. Instead, Neptune is a furnace. Something deep inside the planet is generating enormous amounts of heat, more heat than the Sun provides. This internal energy drives the fastest winds in the solar system, powers the massive storm systems, and creates an atmosphere in constant, violent motion. But where does this energy come from? Scientists don't fully know. When Voyager 2 measured Neptune's heat output in 1989, the results were surprising. Neptune radiates approximately 0.433 watts per square meter from its interior, about 1.4 times the solar energy it receives. This internal heat flux might not sound like much, but spread across Neptune's entire surface, it amounts to roughly 2.4 times 10 to the 17th watts of power. That's 240 petawatts, roughly 1,000 times humanity's total energy consumption. Comparison: Earth radiates almost no excess heat from its interior. The heat flowing out from Earth's core and mantle amounts to only about 47 terawatts, nearly 5,000 times less than Neptune's internal power output, despite Earth being much closer to the Sun. The gas giants Jupiter and Saturn also radiate excess internal heat. Jupiter radiates about 1.7 times the solar energy it receives. Saturn radiates roughly 1.8 times its solar input. But Neptune's situation is more extreme. It's much farther from the Sun than Jupiter or Saturn, receiving far less solar energy. Yet its internal heat output is proportionally larger. Even more puzzling, Uranus, Neptune's near twin in size and composition, radiates almost no excess heat at all. Uranus's internal heat flux is approximately 1.06 times its solar input, barely above zero. Why would two planets so similar in mass, composition, and structure have such radically different internal heat outputs? For the gas giants Jupiter and Saturn, scientists have a reasonable explanation for internal heat. These planets are still slowly contracting under their own gravity. As they contract, gravitational potential energy converts to heat, the same process that keeps Earth's core hot. Jupiter and Saturn haven't finished cooling down from their formation 4.6 billion years ago. Additionally, Saturn may have another heat source, helium rain. Deep inside Saturn, helium separates from hydrogen and forms droplets that sink toward the core, releasing gravitational energy as heat. This process might contribute significantly to Saturn's excess luminosity. But Neptune is much smaller than Jupiter or Saturn. Its gravitational contraction should have ended long ago. The heat left over from Neptune's formation billions of years ago should have radiated away into space. Yet Neptune is still radiating significant heat. One theory suggests that Neptune's interior hasn't fully differentiated yet, meaning heavier elements are still slowly sinking toward the core, releasing gravitational potential energy as heat. This process would be ongoing even billions of years after formation if Neptune's interior has remained partially mixed. The November 2024 discovery of phase separation in Neptune's interior supports this idea. If water, methane, and ammonia are continuously separating into layers, and if diamonds are forming and sinking through these layers, these processes would release energy. Diamond formation is exothermic. It releases heat. As carbon atoms bond together to form diamond crystal structures, they release energy into the surrounding material. On Neptune, where diamond rain may be falling continuously through thousands of kilometers of atmosphere and interior, this could represent a significant heat source. Furthermore, as diamonds sink through the convecting water-rich layer, they experience friction. The friction between sinking diamonds and the surrounding fluid converts their gravitational potential energy into heat, adding even more thermal energy to Neptune's interior. Laboratory experiments conducted in January 2024 by Mungo Frost's team at SLAC National Accelerator Laboratory confirmed that diamond formation from hydrocarbons releases substantial energy. When they simulated Neptune's interior conditions using lasers and plastic samples, the rapid diamond formation they observed generated measurable heat. Scaled up to planetary dimensions, this process could potentially explain Neptune's excess luminosity. But the diamond rain theory doesn't explain why Uranus lacks significant internal heat. Uranus should have similar diamond formation processes occurring in its interior. Yet Uranus barely radiates excess heat at all. The leading explanation for Uranus's coldness involves a massive impact early in the solar system's history. Computer simulations suggest that an Earth-sized object collided with Uranus billions of years ago. This impact would have two major effects. First, it would knock Uranus onto its side, explaining the planet's 98-degree axial tilt. Second, it would deposit a massive amount of material around Uranus's core. This material would form an insulating layer that dramatically slows heat transfer from the core to the outer parts of the planet. Heat generated in the core takes much longer to reach the surface, so Uranus radiates less heat into space, even though its interior might be quite hot. Neptune apparently avoided such a catastrophic impact. Without an insulating layer, heat from Neptune's interior can reach the surface more efficiently. The difference in internal heat between Neptune and Uranus has profound atmospheric consequences. Neptune's internal heat drives vigorous convection throughout its atmosphere. Hot material rises from deep in the planet, cool material sinks, creating powerful circulation patterns. These convection cells generate the wind shear that produces Neptune's massive storm systems. The internal heat also explains Neptune's extreme wind speeds. The fastest winds on Neptune reach 2,100 kilometers per hour at the equator, far exceeding wind speeds on Jupiter, despite Jupiter receiving more solar energy. These winds are driven from below by internal heat, rather than from above by solar heating. The internal energy creates temperature differences between different atmospheric layers and different latitudes, and these temperature differences drive winds. Uranus, lacking significant internal heat, has much calmer weather. Wind speeds on Uranus reach a maximum of about 900 kilometers per hour, fast by Earth standards, but sluggish compared to Neptune. Uranus also lacks the dramatic storm systems observed on Neptune. No great dark spots have been observed on Uranus. Its atmosphere appears relatively featureless in most observations, with only subtle banding and occasional small storms. Internal heat difference also affects atmospheric chemistry. On Neptune, strong convection brings gases from deep in the atmosphere up to higher, cooler levels where they can condense and form clouds. This creates the dynamic cloud activity observed by Hubble and other telescopes. On Uranus, weaker convection means less vertical mixing. Gases tend to remain stratified at the altitudes where their temperature and pressure conditions are stable. This creates a hazier, more uniform appearance. Neptune's internal heat is also responsible for making the planet detectable in infrared wavelengths. When astronomers observe Neptune with infrared telescopes, they're seeing both reflected sunlight and thermal emission from the planet itself. The thermal emission comes from the internal heat radiating through the atmosphere. This internal thermal emission is what allowed the James Webb Space Telescope to observe Neptune so clearly in the near-infrared. Webb could see Neptune's cloud structure, atmospheric bands, and even the auroral emissions, partly because Neptune is glowing in infrared light from its own internal heat. But despite decades of study and recent breakthroughs in understanding Neptune's interior structure, the fundamental question remains unanswered. Why does Neptune radiate so much more energy than it receives from the Sun? Is it primarily diamond rain releasing gravitational energy? Is it ongoing differentiation as materials separate into layers? Is it residual heat from formation that somehow hasn't dissipated? Is it some combination of all these processes? Scientists don't have a definitive answer yet. What they do know is that Neptune's internal heat is one of the key factors making it such a dynamic, violent world. Without this internal energy source, Neptune would be cold and dead like Uranus, a pale, nearly featureless ball of gas drifting at the edge of the solar system. Instead, Neptune is alive with activity. Its internal furnace drives weather systems, powers winds, generates storms, and creates an atmosphere in constant motion. And that internal heat is intimately connected to everything scientists have discovered about Neptune's interior in 2024. The phase separation creating layered interiors, the aquadium ions conducting electricity, the diamond rain falling through superionic water oceans, the convection driving the chaotic magnetic field. All of these processes are connected. They're all part of Neptune's internal engine, converting gravitational potential energy into heat and motion. Understanding this engine requires understanding Neptune's internal structure, the layers hidden beneath those pale greenish-blue clouds where no spacecraft has ever ventured and no telescope can see. Neptune is not what it appears to be. From the outside, Neptune looks like a uniform ball of gas. Its atmosphere appears smooth, with subtle banding and occasional storms. But appearances deceive. Beneath those outer clouds lies a world of extremes, crushing pressures, scorching temperatures, exotic states of matter that can't exist on Earth. Neptune is classified as an ice giant, a term that misleads people who imagine a planet made of frozen water. There's no ice in the sense of solid frozen water anywhere on Neptune. The ice in ice giant refers to volatiles, materials like water, methane, and ammonia that were ices in the early solar system but exist in completely different states under Neptune's interior conditions. The structure of Neptune can be divided into several distinct layers. The outermost layer is the atmosphere. This consists primarily of molecular hydrogen, H2, making up about 80% of the atmosphere by volume. Helium accounts for roughly 19%. The remaining 1% includes methane, CH4, which gives Neptune its color, plus trace amounts of hydrogen deuteride, ethane, and other gases. The atmosphere extends down from the cloud tops to depths of several thousand kilometers. Temperature and pressure increase with depth. At the visible cloud tops, temperatures are around 55 Kelvin, -218 degrees Celsius. Pressure is roughly 1 bar, similar to Earth's atmospheric pressure at sea level. As depth increases, temperature rises to around 7,000 Kelvin and pressure reaches several million bars. These are the conditions where the atmosphere transitions into the mantle. The mantle is where Neptune's interior gets truly strange. This layer consists of water, methane, and ammonia under extreme pressure and temperature. These materials exist in states that don't occur naturally on Earth: superionic ices, dense fluids, and polymeric structures. Superionic ice is one of the most exotic materials in Neptune's mantle. In this state, oxygen atoms from water molecules form a crystalline lattice structure, solid like ice, while hydrogen ions flow freely through this lattice like a fluid. The result is a material that's simultaneously solid and liquid. The oxygen lattice is rigid enough to maintain its structure, but the hydrogen ions can conduct electricity as they flow, making superionic ice an electrical conductor despite being ice. Superionic ice only forms under extreme pressure and temperature conditions. On Earth, scientists have only recently managed to create superionic ice in laboratory experiments using diamond anvil cells and powerful lasers to generate the necessary pressures, millions of atmospheres. But in Neptune's mantle, these conditions persist throughout billions of cubic kilometers of the planet's interior. Vast oceans of superionic water exist at depths below about 10,000 kilometers. The 2024 breakthroughs revealed that Neptune's mantle isn't uniform. Instead, it's stratified into layers. The upper mantle, roughly 3,000 to 10,000 kilometers deep, is water-rich. This layer convects vigorously. Hot material rises from below, cools as it rises, and sinks back down in a continuous circulation pattern. This convecting water layer is where Neptune's magnetic field originates. The water contains dissolved ions, including the exotic aquadium discovered in 2024. As the conducting fluid convects, it generates electrical currents, and these currents produce the magnetic field. The lower mantle, below about 10,000 kilometers, is rich in carbon, nitrogen, and hydrogen. This material has undergone phase separation from the water-rich upper layer. Under the intense pressures of the lower mantle, methane and ammonia break down. Carbon and nitrogen atoms form complex polymeric chains, long molecules consisting of carbon-nitrogen backbones with hydrogen atoms attached. This polymeric material is denser than the water-rich material above it, so it remains stratified below the convecting layer. Crucially, it doesn't convect efficiently and doesn't contribute to magnetic field generation. The boundary between these layers, around 10,000 to 12,000 kilometers deep, is where diamond formation occurs. As methane and other hydrocarbons from the upper layer sink into regions of higher pressure, carbon separates from hydrogen. The carbon atoms bond together, forming diamond crystal structures. These diamonds then sink through the lower mantle, pulled downward by gravity. The January 2024 experiments by the Frost team showed that diamond formation can occur rapidly, within nanoseconds under the right conditions. On Neptune, where these conditions persist for billions of years, diamonds would have ample time to grow. Starting as nanodiamonds, crystal structures just a few nanometers across, they would aggregate as they sink, growing into larger and larger crystals. By the time diamonds reach the deepest parts of the mantle, they might be enormous, potentially meters across and weighing millions of carats. At even greater depths, below about 20,000 kilometers, conditions become extreme even by Neptune standards. Temperatures might reach 7,000 Kelvin. Pressures exceed 700 gigapascals, 7 million times Earth's atmospheric pressure. Some theoretical models suggest that at these depths, diamonds themselves might melt, forming a layer of liquid carbon. In this scenario, solid diamonds would float on the surface of a liquid carbon ocean, like icebergs on Earth's oceans. Other models suggest diamonds remain solid all the way down to Neptune's core, but accumulate in a thick shell around the core, a diamond layer potentially thousands of kilometers thick. At Neptune's center lies the core, a ball of rock and metal roughly Earth-sized. The core consists primarily of silicates, silicon and oxygen compounds, along with iron and nickel. It's similar in composition to Earth's mantle and core, but compressed to much higher density by the immense pressure of the layers above. The core's temperature might reach 7,000 to 8,000 Kelvin, hotter than the surface of the sun. But despite this intense heat, the core is solid because the pressure is so extreme that atoms can't move freely enough to melt. The core accounts for only about 15% of Neptune's mass. The vast majority of the planet's mass is in the mantle, those exotic layers of water, methane, ammonia, polymeric materials, and diamonds. This internal structure explains many of Neptune's observed properties. The high density of Neptune, 1.63 grams per cubic centimeter, indicates that Neptune has more rock and metal in its interior than Uranus, which has a density of only 1.27 grams per cubic centimeter. Neptune's core is proportionally larger or denser than Uranus's core. The heat output, 2.6 times solar input, comes from ongoing processes in the mantle. Diamond formation releases energy. Sinking diamonds release gravitational potential energy. Ongoing phase separation between water and carbon-rich materials releases energy as these materials chemically reorganize. The chaotic magnetic field originates in the thin convecting water layer, where electrical currents are generated by moving ions, including aquadium. The violent atmospheric activity is driven by heat flowing upward from the internal layers, creating temperature differences that drive winds and storms. Understanding Neptune's interior structure has implications beyond just understanding Neptune itself. Neptune-sized planets are common throughout the galaxy. As of 2025, thousands of exoplanets have been discovered with masses and sizes similar to Neptune. These planets orbit other stars throughout the Milky Way. Many exoplanets are even in the mini-Neptune category, larger than Earth but smaller than Neptune, a planetary type that doesn't exist in our solar system. When astronomers study these distant Neptune-like worlds, they can only observe their masses, sizes, and sometimes their atmospheric compositions. They can't directly see inside these planets. But by understanding Neptune's interior, how materials phase separate under pressure, how diamond rain forms, how layered interiors generate magnetic fields, scientists can infer what's happening inside these distant exoplanets. If an exoplanet has a chaotic magnetic field, scientists can now reasonably infer it probably has a layered interior similar to Neptune. If it radiates excess heat, diamond rain or other gravitational separation processes are likely occurring. The 2024 discoveries about Neptune's interior represent a major advance in planetary science that extends far beyond our solar system. But Neptune consists of more than just the planet itself. Because orbiting high above these layers of superionic ice and diamond rain are celestial bodies that hold secrets of their own. A system of rings so faint they remained hidden for decades, and a family of moons with histories written in their choice orbits. Neptune has rings, but they're almost impossible to see. For years before Voyager 2's 1989 flyby, astronomers suspected Neptune might have a ring system. Several observations from Earth had suggested something might be blocking starlight as Neptune passed in front of distant stars, a possible indication of rings. But the observations were inconsistent. Sometimes the starlight dimmed as expected. Other times it didn't. The suspected rings seemed to be incomplete or patchy. When Voyager 2 arrived, it confirmed that Neptune does indeed have rings, 5 of them. But these rings are extraordinarily dark and faint, making them extremely difficult to observe from Earth. The rings are composed of particles that reflect only about 2% of the light that hits them. This is darker than coal. Against the black backdrop of space, at Neptune's distance from both the Sun and Earth, these rings are nearly invisible. The innermost ring is named Gala, after Johann Gottfried Gala, who first observed Neptune through a telescope in 1846. The Gala ring is very faint and very wide, about 2,000 kilometers across. Next outward is the Leverrier ring, named after Urbain Leverrier, who calculated Neptune's position. Despite being described as bright compared to the other rings, it's still extremely faint by the standards of Saturn's rings. The Leverrier ring is only 113 kilometers wide. The Lassell ring comes next, named after William Lassell, who discovered Neptune's moon, Triton. This ring is very faint and about 4,000 kilometers wide. At the outer edge of the Lassell ring lies the Arago ring, named after François Arago, who supported Leverrier's work. The Arago ring is slightly brighter than the Lassell ring, but less than 100 kilometers wide. The outermost ring is the Adams ring, named after John Couch Adams, who independently calculated Neptune's position. The Adams ring is about 35 kilometers wide and is one of the brightest, though still extraordinarily faint by absolute standards. The Adams ring contains the most intriguing features: ring arcs. Ring arcs are dense clumps of material within the ring that appear much brighter than the surrounding ring material. These arcs have been named Fraternité, Égalité, Liberté, and Courage, names associated with the French Revolution, honoring Leverrier's French heritage. Ring arcs are unusual. Normally, ring particles spread out uniformly around a planet due to their orbital motion. Any clumping should quickly disperse. Yet Neptune's ring arcs have remained stable since they were first discovered in the 1980s through stellar occultation observations. The stability of these arcs puzzled scientists until they realized that Neptune's moons play a crucial role. Specifically, a small moon named Galatea orbits just inside the Adams ring. Galatea's gravity creates a gravitational resonance with particles in the ring, confining them into arcs, rather than allowing them to spread uniformly. This moon-ring interaction is similar to processes that create gaps and waves in Saturn's rings, but the effect on Neptune produces arcs rather than gaps. Hubble Space Telescope observations in the 1990s and 2000s monitored the ring arcs to see if they were changing. The arcs did show some evolution, slight changes in brightness and position, but they remained stable overall, suggesting their relatively long-lived features. In September 2022, the James Webb Space Telescope captured stunning new images of Neptune's rings in near-infrared wavelengths. These images showed the ring system in unprecedented detail from an Earth-orbiting telescope. When Heidi Hammel, a planetary astronomer who has studied Neptune for decades, first saw the Webb images, she reportedly said they brought her to tears. The clarity and detail of Neptune's ring system, visible in the images, surpassed anything seen since Voyager 2. The Webb images showed not just the main rings, but also faint dust bands between the rings and subtle structures within the rings that had never been visible before. The rings raise questions about Neptune's history. Where did the ring material come from? How long have the rings existed? One theory suggests the rings formed from material ejected when a moon collided with another object, either another moon or a passing comet or asteroid. The shattered moon formed a debris disk that gradually spread into rings. The very dark color of the ring particles supports this origin. If the rings formed from a shattered moon, they would consist of the same dark, carbon-rich material that makes up many of Neptune's small inner moons. Ring lifetimes depend on several factors. Particles constantly collide with each other, grinding down into smaller fragments. Some particles fall into Neptune's atmosphere, removed from the rings. Others might be ejected from the ring system by gravitational interactions. Scientists estimate Neptune's current rings might be relatively young, perhaps only tens of millions of years old, rather than billions of years old like the planet itself. the rings might have formed and dissipated multiple times over Neptune's history. Beyond the rings orbit Neptune's moons, 16 known as of 2025, though more undoubtedly remain to be discovered. The moons fall into two distinct categories: regular moons and irregular moons. Regular moons orbit close to Neptune in nearly circular orbits aligned with the planet's equator. These 7 inner moons likely formed from the disk of material orbiting Neptune during the planet's formation, or from material ejected during Triton's capture. The regular moons are all relatively small. The largest is Proteus, measuring about 420 kilometers across. Proteus is notably not spherical despite its size. It's more potato-shaped with large craters. One crater, Pharos, is so large that it's remarkable the impact that created it didn't shatter the moon entirely. The other inner moons are even smaller: Naiad, Thalassa, Despina, Galatea, Larissa, and Hippocamp. Hippocamp, discovered by Hubble in 2013, is particularly interesting because it might be a fragment knocked off Proteus by an ancient impact. Then comes Triton, Neptune's largest moon and one of the most fascinating objects in the entire solar system. Triton is so important and unique that it deserves its own extended discussion, which is coming shortly. Beyond Triton orbit 9 irregular moons. These moons follow elliptical, inclined orbits, many moving retrograde, backward relative to Neptune's rotation. The irregular moons are almost certainly captured objects, asteroids or Kuiper belt objects that wandered too close to Neptune and were gravitationally captured billions of years ago. The largest irregular moon is Nereid, discovered by Gerard Kuiper in 1949. Nereid follows a highly elliptical orbit that takes 360 days to complete. At its closest, Nereid comes within 1.4 million kilometers of Neptune. At its farthest, it recedes to 9.7 million kilometers, nearly 7 times further away. This extreme orbital eccentricity suggests Nereid's orbit was disrupted during Triton's capture. Computer simulations suggest Triton's arrival in the Neptune system would have gravitationally perturbed any pre-existing moons, flinging some into the outer solar system while stranding others in irregular orbits. The other irregular moons, Halimede, Sao, Laomedea, Samatha, Naso, and 3 unnamed objects designated S2002 N1 through N3, all orbit far from Neptune, taking years to complete single orbits. Samatha and Naso hold the record for the most distant planetary moons in the solar system. They orbit Neptune at distances of about 46 million and 48 million kilometers respectively, more than 120 times further than Earth's moon orbits Earth. These distant moons take 25 years to complete a single orbit. They're tiny, only about 40 kilometers across, and extraordinarily faint. Discovering them required painstaking searches through telescope images, looking for faint points of light that slowly moved against the background stars. In February 2024, astronomers announced the discovery of 2 more moons of Neptune. Using some of the largest ground-based telescopes in the world, including the Subaru telescope in Hawaii, a team led by Scott Shepard at Carnegie Science detected 3 new natural satellites orbiting the outermost planets, 1 around Uranus and 2 around Neptune. The Neptune discoveries were particularly challenging. One of the new moons is extraordinarily faint, the faintest moon ever discovered around Neptune using ground-based telescopes. It required special image processing techniques to reveal the tiny, dim object against the bright glare of Neptune itself. These newly discovered moons are small, probably less than 50 kilometers across. They follow distant, irregular orbits similar to the other outer irregular moons. The fact that new moons continue to be discovered suggests there are probably more waiting to be found. The limitations are purely technological. Neptune is so far away and its outer moons so faint that only the very largest telescopes can detect them. As telescope technology continues improving, more discoveries are likely. There might be dozens of small irregular moons orbiting Neptune that remain too faint to detect with current instruments. The irregular moons provide clues about Neptune's early history. If Triton was captured from the Kuiper Belt, other Kuiper Belt objects might have been captured as well. Some irregular moons might be captured Kuiper Belt objects, preserving primordial material from the solar system's formation. Studying these moons' orbits also reveals information about past gravitational interactions in the Neptune system. Moons with similar orbital characteristics might be fragments from a larger parent body that was shattered by a collision. The 2024 research noted that the irregular moons show orbital groupings, moons with similar orbits to each other, suggesting they share a common origin. At Neptune, some outer moons group together in orbital families, hinting that they're pieces of larger moons that were destroyed by impacts with comets or asteroids. But of all Neptune's moons, one stands utterly apart. One moon that's not really a moon at all, but a captured dwarf planet following a backward orbit around Neptune, while holding secrets about the outer solar system's history and possibly harboring conditions suitable for life beneath its frozen surface. That moon is Triton. Triton is backwards. Every large moon in the solar system orbits in the same direction as its planet rotates. Earth's moon orbits counterclockwise as viewed from above Earth's north pole, matching Earth's counterclockwise rotation. Jupiter's large moons orbit counterclockwise, matching Jupiter's rotation. Saturn's, Uranus's, all the same. Except Triton. Triton orbits Neptune clockwise, retrograde, opposite to Neptune's counterclockwise rotation. This retrograde orbit immediately reveals that Triton did not form alongside Neptune. It's an outsider, a captured object that once orbited the Sun independently before Neptune's gravity ensnared it. Triton is also tilted. Its orbital plane is inclined 157 degrees to Neptune's equator, more than a right angle. This extreme inclination, combined with the retrograde motion, means Triton is essentially orbiting Neptune upside down and backwards. No other large moon in the solar system has such a bizarre orbit. Triton's size adds to its remarkableness. At 2,710 kilometers in diameter, Triton is the 7th largest moon in the entire solar system. It's larger than Pluto, larger than the dwarf planet Eris, larger than any object definitively known to exist in the Kuiper Belt. Triton is not just Neptune's largest moon. It accounts for 99.5% of all the mass orbiting Neptune. The other 15 moons combined contribute only 0.5%. Triton's mass is so dominant that it appears in Neptune's sky at roughly the same angular size as Earth's moon appears from Earth, despite being slightly smaller in actual diameter. Triton orbits closer to Neptune than Earth's moon orbits Earth, only 355,000 kilometers, compared to the moon's 384,000 kilometers. Where did Triton come from? The retrograde orbit and extreme inclination prove Triton formed elsewhere and was later captured. The most likely origin, the Kuiper Belt, the region beyond Neptune containing thousands of icy bodies left over from the solar system's formation. When NASA's New Horizons spacecraft flew past Pluto in July 2015, it discovered that Pluto and Triton are remarkably similar. Both have surfaces composed primarily of nitrogen ice, with water ice and other volatiles mixed in. Both have similar densities, about 2 grams per cubic centimeter. Both have thin nitrogen atmospheres. Both show evidence of active geology despite being incredibly cold. A 2024 study comparing the chemical compositions of Triton and Pluto found strong evidence that both objects originated in the same region of the outer solar system before Triton was captured by Neptune. This makes Triton not just Neptune's moon, but the largest known Kuiper Belt object, bigger than Pluto, the former 9th planet that gave the Kuiper Belt objects their informal name, Plutinos. But how did Neptune capture such a large object? Objects orbiting the Sun carry enormous angular momentum. For Neptune to capture Triton, that angular momentum had to go somewhere. The leading theory involves a 3-body interaction. Triton probably wasn't orbiting alone. Like Pluto and its moon Charon, Triton might have been part of a binary system, two objects orbiting their common center of mass while both orbited the Sun. When this binary system encountered Neptune, the gravitational interaction would have been catastrophic. Neptune's enormous gravity would pull on both objects, but unequally. One object, Triton, would lose orbital energy and be captured into orbit around Neptune. The other object would gain energy and be flung away, possibly ejected from the solar system entirely. This three-body interaction can efficiently capture one member of a binary pair while ejecting the other, solving the angular momentum problem. Computer simulations show this process could have captured Triton into a highly elliptical initial orbit. Over millions of years, tidal forces from Neptune would circularize the orbit, bringing it to the nearly circular orbit observed today. The circularization process would have dramatic effects on Triton itself. As Triton moved through its initial elliptical orbit, Neptune's gravity would alternately stretch and compress the Moon, tidal flexing. This flexing generates enormous amounts of heat through friction. Just like bending a paperclip back and forth rapidly makes it hot. New research published in September 2024 in the Planetary Science Journal by Nate Hammond and Jeffrey Collins showed that tidal heating from orbit circularization could have kept Triton warm and active for billions of years, far longer than previously thought. The study revealed that internal feedbacks between tidal heating and ice shell melting significantly slow down the orbital evolution. As tidal heating melts the ice shell, making it thinner and more fluid, it actually reduces the rate at which the orbit circularizes. This creates a self-regulating system that maintains strong tidal heating over extended periods. The implications are profound. Triton could have had a thin ice shell and vigorous geological activity for billions of years after its capture, rather than just a few 100 million years as earlier models suggested. This extended period of tidal heating would have melted Triton's interior, creating a subsurface ocean beneath the ice crust. And that ocean might still exist today. When Voyager 2 flew past Triton on August 25, 1989, it captured images showing a world unlike any other. Triton's surface is remarkably young. Crater counts suggest the surface is only 10 to 100 million years old, incredibly young by solar system standards. This youth indicates that geological processes are resurfacing the Moon, covering up ancient craters with fresh material. The surface shows diverse terrain types. There's the cantaloupe terrain, regions where the surface has a dimpled, melon rind-like texture, created by what appears to be diaporism, where warm ice rises through colder ice like bubbles in lava lamps. There are smooth plains where liquid material has flowed across the surface and frozen. There are ridges, troughs, and depressions indicating tectonic activity. The surface color is predominantly pinkish or reddish-brown. This coloration comes from tholins, complex organic molecules created when ultraviolet light from the sun strikes methane and nitrogen, transforming them into larger hydrocarbon compounds. Tholins give Triton's surface its distinctive hue, similar to the coloration seen on Pluto. But the most remarkable discovery Voyager 2 made was the plumes. As Voyager 2 approached Triton, scientists spotted dark streaks on the surface, some extending more than 150 kilometers. These streaks appeared to be deposits left by active geyser-like eruptions. Then Voyager captured something extraordinary. Images showing active plumes erupting from Triton's surface, reaching heights of 8 kilometers and trailing sideways due to high-altitude winds. These plumes are almost certainly cryovolcanic, eruptions of volatiles from beneath the surface. But the mechanism might be different from liquid water cryovolcanism seen on other moons. One theory suggests a solid-state greenhouse effect. Triton's surface consists of transparent nitrogen ice overlying darker material. Sunlight penetrates the transparent ice and heats the darker material beneath. This heating sublimates nitrogen ice from below, building pressure in pockets beneath the surface. Eventually, the pressure becomes great enough to fracture the overlying ice, causing an explosive release that carries both nitrogen gas and darker particles high into the atmosphere. A similar process occurs on Mars's seasonal polar caps, where solid carbon dioxide ice traps heat beneath it, eventually explosively sublimating and creating dark, fan-shaped deposits. But some scientists think Triton's plumes might have a deeper origin: water from a subsurface ocean forcing its way through the ice shell, similar to the plumes observed on Saturn's moon Enceladus and possibly Jupiter's moon Europa. If Triton has a subsurface ocean, it would be one of the most distant, potentially habitable environments in the solar system. The conditions for life as we know it include liquid water, organic compounds, and an energy source. Triton might have all three. Liquid water. If tidal heating and radioactive decay from Triton's rocky core provide enough heat, a liquid water ocean could exist beneath the ice shell. The September 2024 study suggests such an ocean could have persisted for billions of years. Organic compounds. Tholins on the surface prove that complex organic chemistry is occurring. If cryovolcanic processes bring material from the subsurface to the surface, organic compounds from the ocean could be present in the surface ice. Energy source. Tidal heating provides energy. Chemical reactions between water and rock in the subsurface could provide additional chemical energy, similar to hydrothermal vents on Earth's ocean floors that support ecosystems independent of sunlight. The possibility that Triton might harbor life makes it one of the highest priority targets for future exploration. Several mission concepts have been proposed to return to Neptune and study Triton in detail. The Trident mission concept, proposed in 2019 and 2021 as a NASA Discovery Program mission, would have conducted a flyby of Triton, mapping its surface, studying its atmosphere, and searching for evidence of a subsurface ocean using magnetometer and gravity measurements. Trident wasn't selected for funding, but the concept demonstrated that a Triton mission is technically feasible with current technology. More ambitious concepts include orbiters that would circle Neptune and conduct multiple Triton flybys, or even landers that would touch down on Triton's surface. The Triton Ocean World Surveyor, proposed in 2024, would launch in 2031 and arrive in 2047. The mission would study both Neptune and Triton, with particular focus on determining whether Triton has a subsurface ocean and whether that ocean might be habitable. Another concept, Nautilus, would launch in 2042 and arrive in 2057, using similar mission architecture. These extended timelines reflect the challenge of reaching Neptune. Even with gravity assists from Jupiter, the journey takes 15 to 20 years. The spacecraft must carry enough fuel and power to operate for decades in the cold, dark outer solar system. But the scientific payoff would be enormous. Triton represents a Kuiper Belt object that can be studied up close. Most Kuiper Belt objects are too distant and too faint to observe in detail. Triton, captured into orbit around Neptune, provides a much more accessible target while preserving the primordial composition of Kuiper Belt material. Triton might be an ocean world, joining the select group of moons that could potentially harbor life beneath their surfaces. Confirming this would revolutionize astrobiology, and Triton's active geology, cryovolcanism, and interaction with Neptune's magnetosphere make it a dynamic laboratory for understanding processes that might occur on icy worlds throughout the galaxy. Neptune's moon system, from its faint, dark rings to its scattered family of irregular moons to the magnificent captured world of Triton, tells a story of violence and capture in the early solar system. A story where Neptune's gravity disrupted binary systems, captured massive objects, and created one of the most intriguing destinations in the solar system. But the story of Neptune isn't just about the past. It's also about the present. Because even now, Neptune's family continues to grow as astronomers discover more moons with increasingly powerful telescopes. And it's about the future. because humanity's next chapter of exploring Neptune and its moons remains to be written. 36 years have passed since Voyager 2's flyby of Neptune. In that time, humanity has sent spacecraft to every other planet in the solar system. Multiple missions have orbited and explored Mars. The Cassini spacecraft spent 13 years orbiting Saturn. Juno is currently studying Jupiter. New Horizons flew past Pluto. Multiple spacecraft have visited Mercury and Venus. But Neptune? Silence. No spacecraft has returned to Neptune since that brief August day in 1989 when Voyager 2 raced past at 54,000 kilometers per hour, capturing what images it could during its short window of observation. The ice giants, Neptune and Uranus, remain the least explored planets in the solar system. This lack of exploration has profound consequences. Scientists must rely on limited Voyager 2 data, now decades old, supplemented by occasional observations from Hubble, Webb, and ground-based telescopes. Every discovery about Neptune's color, magnetic field, interior, structure, atmospheric dynamics, and moons comes with uncertainties and unanswered questions. Without a spacecraft at Neptune making detailed measurements over extended periods, scientists are working with incomplete information. But that may be changing. In April 2023, the National Academy of Sciences released its Planetary Science and Astrobiology Decadal Survey, a comprehensive report outlining priorities for NASA's planetary exploration program over the next decade. The report ranked a Uranus orbiter and probe as the highest priority large mission for the 2033 to 2043 timeframe. While this prioritizes Uranus over Neptune, it represents a crucial shift. The ice giants have finally become a top priority for exploration. A Uranus mission would provide critical information applicable to Neptune. The two planets are similar enough that understanding one helps understand the other, particularly regarding interior structure, atmospheric dynamics, and magnetic field generation. But Neptune-specific mission concepts are also under development. The Neptune Odyssey mission concept, studied beginning in April 2021, envisions a Neptune orbiter with strong focus on Triton. The spacecraft would launch in 2033 and arrive at Neptune in 2049, a 16-year journey. Neptune Odyssey would orbit Neptune for several years, conducting dozens of Triton flybys while also observing Neptune's atmosphere, magnetosphere, and ring system. The mission would address fundamental questions about ice giant formation, interior structure, atmospheric dynamics, and whether Triton harbors a subsurface ocean. Two lower-cost mission concepts followed: Triton Ocean World Surveyor and Nautilus, both targeting launch in the 2030s or early 2040s. The Arcanum mission concept, proposed in 2024, takes a more ambitious approach. It would consist of three components: an orbiter called Somerville to study Neptune, an orbital maneuvering vehicle called Hamilton to adjust trajectories, and a lander named Bingham to touch down on Triton's surface. Arcanum would use SpaceX's Starship rocket, which can lift far more mass than traditional rockets. This increased capacity would enable a more comprehensive mission with multiple spacecraft components. The lander would carry instruments to study Triton's surface composition, search for organic compounds, measure seismic activity to probe the interior structure, and test whether a subsurface ocean exists beneath the landing site. Another concept called TUNE, Triton Unveiler and Neptune Explorer, includes an orbiter and an atmospheric probe. The probe, named Piano, Probe for Inner Atmospheric Neptune Observations, would be released to descend through Neptune's atmosphere, measuring temperature, pressure, composition, and wind speeds as it falls. Such an atmospheric probe would be the first to enter a giant planet's atmosphere since the Galileo probe descended into Jupiter in December 1995. Direct measurements from within Neptune's atmosphere would revolutionize understanding of ice giant atmospheres and test models of atmospheric chemistry and dynamics. China has also expressed interest in Neptune exploration. Chinese space officials have discussed proposals for a Neptune mission that could launch as early as 2033, potentially beating Western missions to the planet. A Chinese Neptune mission would likely include an orbiter and possibly a Triton flyby component. Details remain preliminary, but China's growing space capabilities make such a mission plausible. The international competition might actually accelerate Neptune exploration. If China commits to a Neptune mission in the early 2030s, it could spur NASA and ESA to accelerate their own programs to avoid being beaten to this milestone. But all these missions face significant challenges. First, the journey time. Even with Jupiter gravity assists, reaching Neptune requires 12 to 16 years of travel. The spacecraft must be built to survive that long in the harsh environment of space without maintenance or repair. Second, power. At Neptune's distance, solar panels are nearly useless. The sun is too dim to provide sufficient power. All Neptune missions must use radioisotope thermoelectric generators, RTGs, nuclear power sources that generate electricity from radioactive decay. RTG production is limited. The United States has only a small supply of plutonium-238, the isotope used in RTGs. Each mission to the outer solar system competes for this scarce resource. Third, cost. Missions to Neptune are expensive. A flagship-class Neptune orbiter would cost $3 to $5 billion over its lifetime. Even Discovery-class flyby missions like Trident cost approximately $1 billion. These costs must compete with other priorities: Mars sample return, a Venus flagship mission, continued lunar exploration, asteroid missions, and missions to Jupiter's and Saturn's moons. Fourth, political will. Space missions require sustained funding over decades. A mission launching in 2033 and arriving in 2049 needs political and budgetary support across multiple presidential administrations and Congress terms. Past ice giant mission concepts have been proposed and postponed repeatedly. In 2000, a Neptune orbiter concept was studied but not funded. In 2010, proposals emerged but weren't selected. In 2021, Trident was proposed but lost out to missions to Venus. The pattern of proposals without funding has continued for 25 years. But the 2023 Decadal Survey prioritization of Uranus represents a potential breakthrough. With formal endorsement from the scientific community and clear prioritization in the Decadal Survey, an ice giant mission has the strongest support it has ever had. NASA's preliminary planning suggests a Uranus mission could receive formal approval and funding authorization in the mid-2020s, with development beginning in the late 2020s and launch in the early 2030s. If this timeline holds, the mission would arrive at Uranus in the late 2040s, more than 60 years after Voyager 2's flyby. A Neptune mission would likely follow Uranus, potentially launching in the late 2030s or early 2040s and arriving in the 2050s or beyond. This means scientists currently in graduate school or early career positions could be retired by the time Neptune data arrives. Current graduate students will be in their 60s or 70s when humanity finally returns to Neptune. The extended timelines highlight both the challenges of outer solar system exploration and the importance of starting now. Every year of delay pushes arrival dates further into the future. Starting a Neptune mission program today means arrival in the 2040s or 50s. Waiting another decade means arrival in the 2060s. But when a mission does arrive, whether in 2049 or 2057 or later, the scientific payoff will be transformative. A Neptune orbiter would observe the full planet over multiple years, tracking how storms form and dissipate, measuring atmospheric circulation patterns, monitoring seasonal changes as Neptune moves through its long orbit. It would map Neptune's magnetic field in detail, testing theories about its generation mechanism and studying how the chaotic field interacts with the solar wind. It would observe Neptune's rings continuously, watching how they evolve and searching for mechanisms that maintain the ring arcs. It would fly past Triton dozens of times, mapping the surface in high resolution, measuring the thickness of the ice shell, searching for evidence of a subsurface ocean, analyzing the composition of surface materials and plumes. It would discover new moons too small or faint for ground-based telescopes to detect. It would transform Neptune from a poorly understood distant world into a fully characterized planet with comprehensive data comparable to what scientists have for Jupiter and Saturn. And critically, it would provide the data needed to understand Neptune-like exoplanets throughout the galaxy. Thousands of Neptune-sized exoplanets orbit other stars. With detailed understanding of our solar system's Neptune, scientists could interpret observations of those distant worlds with far greater confidence, determining which have subsurface oceans, which have diamond rain, which have habitable moons. The exploration of Neptune isn't just about one planet. It's about understanding an entire class of planets that dominate planetary populations throughout the Milky Way. Until humanity returns to Neptune, scientists must continue working with limited data, making the most of Voyager 2's brief observations, supplemented by remote sensing from Hubble, Webb, and ground-based telescopes. But the discoveries of 2024 and 2025, the true color revelation, the magnetic field breakthrough, the diamond rain confirmation, the auroral detections, the new moons, demonstrate that even from Earth, major advances in understanding Neptune are possible. As technology improves, even more discoveries will come from telescopes. The next generation of extremely large ground-based telescopes, the 30-meter telescope, the giant Magellan telescope, the extremely large telescope, will have resolving power rivaling Hubble and Webb, allowing detailed atmospheric monitoring from Earth. But ultimately, truly understanding Neptune requires returning with spacecraft. The question is not if humanity will return to Neptune, but when. And whether that return happens in the 2040s, 2050s, or beyond depends on decisions being made right now. The ice giants wait at the edge of the solar system, keeping their secrets. But after 36 years of neglect, they've finally become a priority. Neptune's time is coming. So what didn't they teach in school about Neptune? They didn't teach that for 35 years, every picture of Neptune was wrong. That the deep blue planet of textbooks and documentaries was an enhanced image, artificially colored to show activism features more clearly. That Neptune is actually pale greenish blue, nearly identical to Uranus. They didn't teach that Neptune's magnetic field shouldn't exist according to conventional planetary physics. That the field is tilted 47 degrees and generated in a thin shell rather than the core. That exotic molecules called aquadium, impossible to create on Earth, exist deep inside Neptune, conducting electricity and generating the chaotic magnetic field. They didn't teach that Neptune's interior is separated into layers like oil and water. That water-rich material floats on top of carbon-rich polymeric fluids. That at the boundary between these layers, diamonds form and rain downward through super-ionic water oceans. Diamonds potentially meters across and weighing millions of carats. They didn't teach that Neptune has Earth-sized storms that appear from nowhere and vanish within a few years. That these storms have never been fully explained. That scientists watched a storm reverse direction in 2020, doing something models predicted shouldn't happen. They didn't teach that in 2025, the James Webb Space Telescope finally captured Neptune's auroras, faint emissions stretching across mid-latitudes rather than concentrated at poles. That Neptune's thermosphere has mysteriously cooled by 300 degrees since 1989. They didn't teach that Neptune radiates 2.6 times more energy than it receives from the sun. That deep inside the planet, an internal furnace generates more heat than solar energy provides. That this heat drives the fastest winds in the solar system, despite Neptune being the planet furthest from the sun. They didn't teach that Neptune has faint, dark rings, so difficult to see that even after Voyager 2 confirmed them in 1989, they remained nearly invisible until Webb finally captured them clearly in 2022. They didn't teach that Neptune's largest moon, Triton, is actually a captured dwarf planet from the Kuiper Belt, bigger than Pluto, orbiting backwards, and possibly harboring a subsurface ocean that has existed for billions of years. That Triton has active geysers erupting nitrogen and dark material 8 kilometers into its thin atmosphere. They didn't teach that scientists are still discovering new moons around Neptune, that 2 more were found in 2024 using ground-based telescopes, that there are probably dozens more too faint to detect yet. They didn't teach that humanity has only visited Neptune once, for a few hours in August 1989, and hasn't returned in 36 years. That all our current knowledge comes from that single flyby, plus occasional glimpses from distant telescopes. But most fundamentally, they didn't teach that Neptune is a world that continuously surprises scientists. That every major discovery about Neptune in recent years has contradicted previous understanding or revealed completely unexpected phenomena. The color everyone knew was wrong. The magnetic field no one could explain finally has an explanation in the form of exotic chemistry. The storms behave in ways that shouldn't be possible. The auroras exist where they shouldn't. The interior structure defies simple models. Neptune has spent the last year rewriting itself. In January 2024, scientists revealed the true color. In May, they discovered aquadium. In November, they explained the magnetic mystery with phase separation and layered interiors. Throughout 2024, they confirmed diamond rain occurs shallower than expected. In March 2025, they detected the elusive auroras. Each discovery answered old questions while raising new ones. Why did the thermosphere cool so dramatically? Why do storms reverse direction? Exactly how much diamond rain is falling through Neptune's interior right now? Does Triton really have an ocean? And if so, could anything live there? Neptune remains profoundly mysterious despite all this progress. The textbook Neptune, the simple ice giant, the last planet, the blue world at the edge of the solar system, never existed. It was always more complex, more violent, more alien than anyone imagined. The real Neptune is a world where water exists as superionic ice, simultaneously solid and liquid, where carbon rain falls as diamonds through exotic fluids, where magnetic field lines tangle in chaotic patterns generated by chemistry impossible on Earth, where wind speeds exceed anything found on planets closer to the Sun despite receiving almost no solar energy. The real Neptune is a laboratory for extreme physics and chemistry, a place where conditions create states of matter and processes that cannot be replicated in any Earth laboratory. The real Neptune is the prototype for understanding thousands of similar planets throughout the galaxy, mini Neptunes and Neptune-sized worlds that appear to be the most common type of planet orbiting other stars. Everything scientists learn about Neptune applies to understanding those distant worlds. Every discovery about diamond rain, layered interiors, magnetic field generation, and atmospheric dynamics helps interpret observations of exoplanets billions of kilometers away. Neptune matters not just for its own sake, but because it represents an entire category of planets that dominate the galaxy's planetary population. And humanity has barely begun to explore it. 36 years after Voyager 2's flyby, Neptune remains the least explored planet in the solar system. Scientists work with data from a brief encounter decades ago, supplemented by telescope observations from billions of kilometers away. But the discoveries of 2024 and 2025 prove that even from this distance, Neptune can still surprise. Even with limited data, breakthroughs are possible. Imagine what scientists could discover with a spacecraft actually there. orbiting Neptune for years, flying past Triton dozens of times, sampling the atmosphere directly, mapping the magnetic field in detail, watching storms form and evolve in real time. Imagine probes descending through Neptune's atmosphere, measuring conditions at different depths. Imagine landers touching down on Triton and drilling through the ice to search for organic compounds from a subsurface ocean. Those missions are possible. The technology exists. The scientific justification is overwhelming. The only missing ingredients are political will and funding. Perhaps missions will launch in the 2030s and arrive in the 2040s. Perhaps China will get there first, spurring a new space race to the ice giants. Perhaps budget constraints will delay missions into the 2050s or beyond. But eventually, humanity will return to Neptune. And when those spacecraft arrive, they'll almost certainly discover that what scientists think they know in 2025 is still incomplete, still partially wrong, still missing fundamental pieces of the puzzle. Because Neptune has a track record of defying expectations. For 35 years, everyone believed Neptune was deep blue. Wrong. For 35 years, no one could explain the magnetic field. Now there's an explanation, but it required discovering exotic chemistry no one predicted. For decades, scientists thought they understood how diamond rain forms. The 2024 experiments showed it happens at different conditions than expected. Neptune keeps proving that assumptions are wrong, models are incomplete, and this distant world still has secrets to reveal. That's what they didn't teach in school about Neptune. They taught the simple version, the comfortable version, where Neptune was just the 8th planet, cold and distant and blue. They didn't teach that Neptune is one of the most enigmatic, violent, and scientifically important worlds in the solar system. They didn't teach that Neptune defies physics, generates impossible magnetic fields, rains diamonds through exotic oceans, and might have a moon harboring life. They didn't teach that everything humanity thought it knew about Neptune was wrong. But now, the truth is emerging. The real Neptune, pale greenish blue, magnetically chaotic, internally layered, violently stormy, possibly hosting life on a captured Kuiper Belt object, is far stranger and more fascinating than the simplified version from textbooks. And this is just the beginning. Because Neptune isn't finished surprising scientists. The discoveries of 2024 and 2025 are opening new lines of investigation. Each answered question reveals deeper mysteries. Each solved puzzle exposes new enigmas. As technology improves and telescopes become more powerful, more discoveries will emerge. As mission concepts develop and funding materializes, spacecraft will eventually return. And when they do, Neptune will undoubtedly reveal phenomena no one currently imagines. That's the nature of exploration. The most important discoveries are the ones that completely upend existing understanding. The ones that force scientists to reconsider fundamental assumptions. Neptune has a remarkable talent for delivering exactly those kinds of discoveries. So what didn't they teach about Neptune? They didn't teach that humanity is only beginning to understand this world. That every confident statement about Neptune comes with uncertainty. That the planet at the edge of the solar system guards secrets that will take decades or centuries to fully uncover. They didn't teach humility. The recognition that despite centuries of telescopic observations and one spacecraft flyby, Neptune remains profoundly alien, fundamentally mysterious, and endlessly surprising. Neptune is not the last planet. It's the final frontier of planetary exploration in our solar system. And its story is just beginning. From a color that was wrong for 35 years to magnetic fields that shouldn't exist. From vanishing storms to ghost auroras. From diamond rain to captured worlds that might harbor life. Neptune has rewritten everything scientists thought they knew. In January 2024, Neptune finally revealed its true color. Not the deep blue of millions of textbooks, but a pale greenish blue, almost identical to Uranus. In May 2024, scientists discovered aquadium, an exotic molecule that exists nowhere on Earth but conducts electricity deep inside Neptune's interior. In November 2024, the magnetic mystery that stumped scientists for 35 years was finally solved. Neptune's interior separates into layers like oil and water. A thin, convecting water layer generates the chaotic magnetic field. Below it, carbon-rich polymers remain magnetically dead. At the boundary between them, diamonds rain continuously through superionic water oceans. In March 2025, the James Webb Space Telescope captured Neptune's auroras for the first time, glowing emissions stretching across mid-latitudes where they shouldn't exist, shining through a thermosphere mysteriously 300 degrees colder than it was in 1989. Every discovery has contradicted what textbooks taught. Every breakthrough has revealed that Neptune is stranger, more violent, more alien than anyone imagined. And the discoveries continue. Right now, telescopes are monitoring Neptune's atmosphere, watching for new storms. Scientists are analyzing data from Webb, searching for chemical signatures in Neptune's spectrum. Researchers are running computer simulations of diamond rain, phase separation, and magnetic field generation. More revelations are coming. But the biggest revelations will come when humanity finally returns to Neptune with spacecraft, when probes descend through those violent winds, when orbiters map the magnetic field in detail, when landers touch down on Triton and drill through the ice. Those missions are being designed right now. Launch dates in the 2030s, arrival dates in the 2040s and beyond. A return to Neptune is coming, and when it comes, everything will change again. Because if 36 years of telescope observations since Voyager 2 could overturn 35 years of accepted wisdom about Neptune's color, magnetic field, and interior structure, imagine what years of detailed spacecraft observations will reveal. Neptune isn't finished rewriting itself. The pale greenish-blue planet at the edge of the solar system, the world of diamond rain and exotic chemistry and backwards moons and impossibly violent weather, is waiting, and humanity is finally ready to uncover its deepest secrets. This is what they didn't teach you in school about Neptune, but this is what scientists are discovering right now. If space discoveries like this excite you, make sure to subscribe. We'll keep bringing you the stories that change how we see the universe. And if there's a mystery or planet you want us to explore next, tell us in the comments. Clear skies, everyone.